Hi everybody, welcome back to the next video about the Kirchhoff's law. So we have already dealt with Kirchhoff's law, especially a type of analysis which is called as the Kirchhoff's current law. The second type of analysis we have also dealt with the Kirchhoff's current law's application as nodal analysis. So in this video, we are going to deal with the third type or second type of law, which is called as Kirchhoff's voltage law, and the type of analysis which is going to deal with the Kirchhoff's voltage law. Let's get into the video. What is this Kirchhoff's law? So we have already seen about the different two types of Kirchhoff's law and the history of Kirchhoff's law. So what is this introduction? It's a pair of laws stating general restrictions on the current and voltage in the electrical circuit. So here we are going to deal with the first type of Kirchhoff's voltage law. So what is this Kirchhoff's voltage law? So we are going to see here in three sections. One is introduction. Second one, what do you call it as the mesh analysis? And third one is the exercise. So what is this introduction to KVL? So Kirchhoff's voltage law is one of the two fundamental laws in electrical engineering, the other being the Kirchhoff's current law. So KVL is a fundamental law as fundamental as conservation of energy in mechanics, for example, because KVL is a really conservation of electrical energy. KVL and KCL are the starting point for analysis of any circuit. So KCL and KVL always hold and are usually the most useful piece of information you will have about a circuit after the circuit itself. Let's get into what is KVL. So the Kirchhoff's voltage law, or in short abbreviation it is called as KVL, states that the algebraic sum of the voltage across any series of branches in a closed loop is equal to 0. That is, summation of V across the branches is equal to 0. That is called as Kirchhoff's voltage law. We will see with an example. So the below is a single loop circuit. The KVL computation is expressed graphically in that voltage. Figure walking around. So what is this? So this is a circuit having a 10-volt supply and three resistances R1, R2, R3 are connected in series. So all the three voltage across the R resistances are taken as VR1, VR2, and VR3. And this is the current assumed direction. So the resulting KVL equation can be written as VR1 plus VR2 plus VR3 minus 10 volt is equal to 0. Or this also can be written as VR1 plus VR2 plus VR3 is equal to 10. So this is according to the Kirchhoff's voltage law. So this is called as a loop law or the path of traversal. The Kirchhoff's voltage equation is obtained by transversing a circuit loop in either direction and writing down the unexchanged the voltage of each element whose positive terminal is first and writing down the negative of every element voltages where the minus sign is first met. The loop must start and end at the same point. It does not matter where you start the loop. Note that a current direction must have been assumed. The assumed current creates an voltage across each resistor and fixes the position of the plus and minus signs so that the passive sign convention is obeyed. The assumed current direction and polarity of the voltage across each resistor must be in agreement with the passive sign convention of KVL analysis to work. The voltage in the loop may be summed in either direction. It makes no difference except to change all the signs in the resulting equation. Mathematically speaking, it's as if the KVL equation is multiplied by -1. See the illustration below. Summation of voltage terms may be done in either direction. The first one is VR1 plus VR2 plus VR3 minus 10 is equal to 0. That is, we are going to take the voltage sources in positive and the voltage of 10 volt, which is from minus to plus, is taken as negative. The resulting equation is what we have given. The second one is the equations can also be written as minus VR1 minus VR2 minus VR3 plus 10 is equal to 0. So here we have taken in the opposite direction. So see the loop, first loop and second loop. So both are in the opposite direction. So the equation becomes different. If the current direction is from positive to negative, then the voltage is see the direction. And if it is from negative to positive, you can see the direction. So the symbols changes over here with respect to plus and minus. So for both the summations, the assumed current direction is always the same. There is no change in the assumed current direction. So assuming the current direction fixes the voltage references. So the resulting equation becomes, see the both the direction of current, so VR1 plus VR2 plus VR3 minus 10 is equal to 0 for the first case where the assumed direction is from positive to negative. When the assumed direction is from negative to positive, the resulting KVL equation is minus VR1 minus VR2 minus VR3 minus 10 is equal to 0. For both the cases shown, the direction of the sum was same. So based on this, we'll be seeing about an analysis called as the mesh analysis in the forthcoming video. With this, I'm signing off. Thank you.